Hi everyone. In the last lecture, we defined first of all Galois extensions. So some finite field extension was called Galois if the degree of the extension equals the number of elements in the group of automorphisms of the extension K over F. So it's Galois if the degree of the extension K over F is equal to the number of automorphisms of K fixing F. Okay, so one direction is true without the Galois assumption. So we proved that if we have any finite field extension, then we always have that the number of automorphisms of K preserving F is less than or equal to the degree. But we can have strict inequality, and we gave some examples. Okay. So we also saw the following pretty useful theorem. Suppose that we have some finite field extension, K over F, then if F is the fixed field of the group of automorphisms of K over F, then we automatically have that the extension is Galois. So if suppose K over F is a finite field extension, if F is in fact equal to the fixed field of aught K over F, then K over F is Galois. Okay, so just be warned that we always have that F is contained in the fixed field, because every automorphism which fixes F, well, obviously the fixed field is going to be bigger than F, but you might not have equality, and in fact we've got an example. If you join the cube root of 2, we've seen that there's only one element in the group of automorphisms fixing Q, so then the fixed field for that example we've already seen has to be the whole field. And, well, so in this case, Q is strictly contained in Q is strictly contained in the fixed field, which is everything. Okay, so we always have this inclusion, but it can be strict. Okay, so this is telling us if F equals the fixed field, then if we have equality here, then our extension is Galois. Okay, so we now prove the converse. So this actually gives you a perfect criteria for when an extension is Galois. It's a proposition. Suppose some field extension is Galois. Then we have that F equals the fixed field of automorphisms of the extension. Okay, then proof. Let L be the fixed field. Then we know, as we've just said, that the fixed field obviously contains F because every automorphism fixing F fixes F. So L contains F, and L is less than K. So we have the following conclusions: F is in L is in K. Further, we know that since L is a fixed field of odd Kf, we know that the degree of the extension K over L is the number of elements in odd K over F by the main theorem proved on Wednesday. So the main theorem we proved on Wednesday was that if we have some subgroup, group of automorphisms, and if we take the fixed field of that group, then the degree of the extension over the fixed field equals the number of elements in the group. And we apply that to the case where the group is automorphisms K fixing F. So this is by the main theorem of Wednesday's lecture. Applied to the group G equals automorphisms of F. So if we just go back to that theorem and apply it to G, then the fixed field was L, so we have the equality up above. Okay, but we also are assuming that K over F is Galois. So we know that the definition of Galois is that the number of elements in the automorphisms equals the degree of the extension. Okay, so if we put these two results together, so first of all we have, using the theorem proved on Wednesday, the number of automorphisms of K over F is the degree of K over the fixed field. Secondly, since we're assuming it's Galois, this number of automorphisms has to be the degree of the extension K over F. So we have now the equality comparing these two equations, we have the equality K over L is K over F. Okay, so comparing, right, so now we use the Tower theorem, or the multiplicativity of degree, to say K over F, right, is K over L, L over F. So by the equation 1, we get K over L. This is the multiplicativity of degree. So putting this back into 1, we get K over L equals K over L, L over F. And canceling K over L, we get that L has degree 1 over F. This means that L which contains F is a vector space of dimension 1 over F. So it must be F itself. It is a vector space of dimension 1 over F, and hence L equals F. Okay. Okay, so we've now proved a bunch of other useful corollaries of this main theorem from Wednesday, which will actually turn out to have been one of the central theorems in field theory. So we have several other useful corollaries of the main theorem from Wednesday. All right, so proposition. Let K be a field and G a finite subgroup. So we take some field and we take G a finite subgroup of the group of automorphisms. Then if we let F be the fixed field of G, then we automatically have, so we take some finite subgroup, we let F be the fixed field, then we have that the group of automorphisms which fixed the field F is exactly equal to G. And further, K is Galois over F. Okay, so let's prove this. So first of all, right, so our setup is we take some subgroup of the group of automorphisms of the field, and then we want to prove that if we take the fixed field of the subgroup, that the group of automorphisms which fix the fixed field is precisely G. Okay, so first of all, each element G in G by definition fixes F. So each element G in G fixes F, which means that by definition, each element gives you an automorphism of K which fixes F. So G is in aut K over F, and therefore G is a subgroup of the group of automorphisms fixing F. Okay. So this is one direction, one inclusion is obvious. It's obvious from the definitions that G is a subgroup of the group of automorphisms K over F. We have to prove the other side. Okay. So to prove that G is in fact the whole group aut K over F, then it's enough to prove that these groups have the same order. If they have the same number of elements, they'll have to be equal. So G is finite by assumption, and therefore it suffices to prove that aut is also finite of the same number of elements. Okay, but since F is a fixed field of G, but now since F is the fixed field of G, then by Wednesday's theorem, we know that K over F, the degree of the extension K over F is exactly equal to the number of elements in G. And we know further that we always have that. So in particular, right, K, so since this is equal to the number of elements in G, and G is finite, this tells us that in particular from this we see that K is finite over F. And now we know that we always have that the number of elements in the group of automorphisms of K over F is less than a degree. So we've seen that we always have this, but by Wednesday's theorem this equals G. So now we have that G is a subgroup of aut K over F, and G has more elements, or at least as many elements as aut K over F, but since it's a subgroup, the only way this is possible is if the order of G equals the order of aut K over F. And G is a group of automorphisms of K over F as required. Okay, so we've proven now that if we take some finite subgroup and let F be the fixed field of that group, then we automatically have that the group of automorphisms equals the group G. Okay. Oh, sorry. So I forgot to prove this last statement about the extension being Galois. Okay, so now let me just say the K over F. So if you put all the pieces together, you see that this means K over F is Galois. So K over F is then Galois. Since F is, by definition, the fixed field of G equals aut K over F. Okay, so we've proven that G equals aut K over F, and by definition, F was the fixed field of G, so this tells us that F is a fixed field of aut K over F, and we know that if the fixed field of automorphisms of an extension is equal to the base field of the extension, then it must be Galois. This is the criterion we just proved. Okay. Okay, so the next thing to prove is that distinct subgroups of the group of automorphisms give different fixed fields. So next, we prove that distinct subgroups of aut K give different fixed fields. Okay, proposition. let G1 and G2 be two distinct subgroups of the group of automorphisms of some field. Now let F1 and F2 be the fixed fields of these two groups. Then we claim that since G and 1 and G2 are different, we claim that this implies F1 and F2 are different. Then so F1, the subfield F1 of K, and the subfield F2 of K are distinct. Okay, proof. Well, if F1, the fixed field F1 equals a fixed field F2, then we have, first of all, that G1. So F1 is a fixed field of G1, and then we know from the previous proposition, we just proved that this implies that G1 is a group of automorphisms of K over the fixed field F1. But if F1 equals F2, then this equals aut K over F2. Which equals now, since F2 is a fixed field of G2, this equals G2 by the previous prop. So F1 being equal to F2 implies G1 equals G2. So if G1 is different from G2, we must have that F1 is different to F2. And this is what we had to prove. Okay. Okay, so the rest of today's lecture, I'm going to begin talking about splitting fields. Okay, so we need one more characterization of Galois extensions. Let F be a field and take some polynomial with entries in that field. Okay, so let's first prove some very simple lemma telling us that a polynomial has a linear factor x minus alpha if and only if alpha is a root. So lemma fx is divisible by some linear factor if and only if by some linear factor x minus alpha if and only if alpha is a root. So fx is divisible by x minus alpha for alpha in the field if and only if f of alpha equals 0. So this proof is very easy, right? So first of all, if f is divisible by some linear factor, then it must have alpha as a root, because if I plug in alpha, then we see it's 0 on the right-hand side. So if f is divisible by a linear factor, then f alpha equals alpha minus alpha g alpha equals 0. So that's one direction. Secondly, suppose that f has a root alpha, then I can divide, I can use a division algorithm. You see that fx equals x minus alpha gx plus rx, where the remainder term has to have degree is either 0 or has degree less than 1 equals the degree of the linear term. So where rx is either 0 or degree of rx is strictly less than 1. So i.e. rx is a constant r. But now plugging in the root alpha gives, well, I'm assuming that 0 equals f of alpha is now alpha minus alpha g alpha plus r. This is 0. So r equals 0. And hence, since the remainder is 0, f is divisible by x minus alpha. Okay, so we just proved that having a root is equivalent to being divisible by a linear factor. Okay, so we now make an important definition telling us that a polynomial can always, after extending a field, be written as a product of linear factors. Okay, so let's start with some definitions. So take some non-zero polynomial. Then first of all, we will define a splitting field as the smallest field containing all the roots of the polynomial, essentially. So a field extension k over f is called a splitting field for the polynomial if the polynomial factors completely into linear factors over the extension field k. So, i.e., if we consider f as an element of kx, it factors completely as a product of linear factors. So the splitting field for f is, so a field extension of f is called a splitting field for fx if, first of all, f factors completely into linear factors over k, and secondly, I want k to be the smallest such field. So further, fx does not factor into linear factors into a product of linear factors for any subfield, proper subfield containing f. Factors for any subfield of k containing f. So k should be the smallest field containing all the roots, essentially. So it's a splitting field if it's an extension such that in this extension, the polynomial splits as a product of linear factors, and secondly, f does not factor into linear factors for any proper subfield of k containing f. So let's do some examples. First of all, Q adjoint root 2 is a splitting field. For x squared minus 2, right? Because over Q adjoint root 2, then I can factor it as a product of linear factors as long as I have root 2 as an element in the field. Okay, so to get the splitting field, you have to add into the field all of the roots of the polynomial, because having a root is equivalent to the polynomial having a linear factor. Okay, another similar example, C is a splitting field. No, C is not a splitting field. Sorry. C contains a splitting field, but sorry, Q adjoint I is a splitting field. Contained in C for x squared plus 1. Okay. Because the root of x squared plus 1 is a complex number I. Okay, so let's prove now that there always exists a splitting field for polynomials over any field. Let f be a field. Take some non-zero polynomial f of x. Then there exists a splitting field k for f of x. Okay, proof. So we first show that there exists some field, maybe not the smallest such field, but there exists a field over which f factors completely into linear factors. So we first show that there is an extension E of f for which f of x factors completely into linear factors. So let n be the degree of fx. Then we argue by induction on the degree. Okay, so first of all, if n equals 1, then f is already linear and there's nothing I need to do. F already splits as a product of linear factors. So if n equals 1, then f is already linear. So we are done. Now suppose n is at least 1. Suppose n is greater than 1. Then if all the irreducible factors of fx over f have degree 1, then we're again done, because I can factor it as a product of irreducibles over f. So if all irreducible factors of f of x over f already have degree 1, then we're done, because f is already a product of linear factors. Then we are already done. So we may assume that we have an irreducible factor of degree at least 2. Okay, so now the extension E1 defined to be f adding in a variable y. So we'll look at the field of polynomials where I'm going to write the variable as y to avoid confusion, divided by the polynomial py. I'm going to replace x by y as a variable for the polynomial p. Now if we look at the field extension E1 given by fy divided by the maximal ideal py, then we know from what we've already seen a couple of weeks ago that this is a field extension of f containing a root of px. So this is an extension of f containing the root alpha defined to be the equivalence class of y, which satisfies the polynomial equation p alpha equals 0, so it's a root of px. Okay. And this is a field extension of degree equal to the degree of the minimal polynomial of alpha, which is p. Okay, so we've seen that this is a field extension. So over the field extension P1, so over the field extension E1, Px now has a factor x minus alpha. Okay, and now since Px was an irreducible factor of f of x, so since Px was an irreducible factor of the polynomial we started with, then the polynomial we started with has a linear factor over the, when considered as an element of E1x, and thus if I apply polynomial division over E1x, I see that the remaining factor of fx when dividing by this linear factor has degree n minus 1. So thus the remaining factor f1x of fx has degree n minus 1. But by induction, so by the induction hypothesis, there is now a field extension of E1 such that f1 factors is a polynomial of linear factors. So by induction, there is an extension E of E1 over which f1 and hence f factors completely into as a product of linear factors. Okay. So thus we've now proven that given any polynomial, I can find some larger field which over which f factors completely as a product of linear factors. Okay, so now to get this, I want the splitting field to be the smallest such field, so I just let it be the intersection of all these fields. So now, once I've taken my, so E, so now we have an extension E of f for which fx factors completely into linear factors. To get the smallest field, I can just take the intersection. Okay, so now let K be the intersection of all subfields of E which contain f and all the roots of the polynomial. Then f will be the splitting field because it will be now the smallest field containing all the roots. Then k will be the splitting field.